Okay, so this is fifth lecture, and this topic is going to be so-called T exactness, of course, Tame Langlands functor. So this is joint work with, it's part of a material in joint work with Ian Gleason and Xiangqian Yang. So it was kind of some, there was some arguments in my previous article, but now I think we actually use some, make that much, organize those much better and prove something much stronger. So this is what we can say. So let me just start by state what is the main result, and then let's recall that last time we said we have, okay, let's assume G unramified, maybe in particular quasi-split, fix all this data, psi from F to, and maybe there's either QL bar or FL bar, but the L, if it's in this case, in the second case, we want to L is sufficiently large. Let's see. At the moment, what else? Right. So in this case, we do have this functor. As we see, we got this functor from shift of the Tame part of this. Get to like inco with unipotent singular support of Tame log of G, G, and this is equivalence. Furthermore, it's equivalence if lambda is a field of characteristic 0. In general, so far we don't know its equivalence, but anyway, it's fully feasible. But on the other hand, there's a natural functor from here to imperf of this guy. Just this is a right adjoint of the natural inclusion. So right adjoint of the inclusion, because perf is inside co, so that you have natural inclusion from imperf into inco, sending compact to compact, so this admits a continuous right adjoint. And then you can compose this. This is what I think follows the notation in David and Lucas series. So right, this is a C side, but maybe here I add everything Tame, probably, to just indicate this part of the story. And then the goal of today's lecture is to see something about, so there's a bunch of goals. First of all, is actually to, maybe let me just state the theorem and then see so the definition. Now I want to say something about it. There's so far this functor C psi is just a functor between derived or infinite categories, and I want to say something about at the level of abelian categories, some T exactness. So for that, I need to first define the T structures on both sides, and the definition of T structure on ISOC is what we call the exotic or exceptional T structure. So this is I will first give the definition and talk more about the motivation later. So we just define a T structure by specify its connective part. It's just those F, such that when you restrict to each strata, which is the representation of GBF. This is in Tame part, and this is actually sits in cohomological degree less than or equal to 2 rho nu B. Nu B is this Newton co-character attached to B, and then you can define also co-connected part to be those F, such that this what I write IB upper sharp of F is inside here, but the greater than equal to rho mu B. So let's wait a little bit later to see this, what this notation is, upper sharp. But to define T structure, actually you only need to define half of it, define the connective part of it. So strictly speaking, I don't need the second line to define the T structure, but I just tell you what it is once we know the connective part. All right, so this is also we can define a T structure on imperf of this is I also want to write this E, and we'll see why. Exceptional T structure on this. So this is basically what Farkshotz called good filtration T structure, although I think they didn't explicitly define on the T structure on imperf of stack of parameters, but it's really just the same thing. This is just those E such that the home from any W lambda to E is inside D less than or equal to here. So this is the W where W lambda is for any lambda, is a while module of highest way lambda. And this is a representation of G hat, of G hat of highest way lambda, and then you regard it as a vector bundle or a vector bundle on the stack of parameters in the usual way. So it's and then you can also define the co-connected part is those E such that the home of the dual of while module, some people also call it the sure module. Okay. This is a dual of while module or sure module.
Are W lambda and S lambda sort of
due to each other, yes, yes. Like S lambda is really just the come from the Borel-Weill theorem. It's like the global section of line bundles on the flag varieties for dominant lambda, and while W is actually it's dual usually. All right, and then the theorem is this is like Gleason, Young, and myself is this C psi is exact, is T exact with respect to source and target T structures. Okay.
just to clarify, lambda is QL bar. This is just the usual T structure.
This is the I'm gonna comment. Yes. So there's actually a bunch of comments, but maybe the first comment is if lambda is QL bar, then this imperf is the same as quasical, and then this exceptional T structure. Exceptional T structure is just a standard T structure on quasical. So okay. Yeah, maybe this remark is let's just make this first remark in this way, and yeah, maybe the second remark is again when Q is there's an analogous theory in geometrical Langlands. So statement in geometrical Langlands. This is proved by, or maybe restricted version of geometrical Langlands. So this is proved by Ruskin and Fragenman. But this also suggests, this theorem actually suggests what should, in geometrical Langlands, I think people haven't talked about modular coefficients. So, but I think this result also suggests what should be the correct statement if you do modular coefficient geometric Langlands. Okay. All right, any questions so far about this? All right, okay, so now let me move to the, talk about the T structure on this Shifa ISA. So, so this is exceptional T structure. Exceptional T structure. Actually, this capacity is a very general content. So let me remind you. So recall from Benison, Bertrand, Delin, McGabber, this is Rickman. Is or maybe people now call semi-orthogonal decomposition, as I mentioned in the first lecture, is following if we're given such data of triangulated categories or stable categories. So you have a bunch of functors. F and G satisfy a bunch of conditions. They all admit left and right adjoint. So satisfying like G composed of F is 0. Then for any X in D in the middle category, we have the following co-fiber sequence, where maps are given by natural adjunction. Okay. Then, so given such data, then if we have a T structure on C and E, we can define T structure on D by gluing T structure. Okay. We get a T structure on D by gluing these two. So this is just those X, maybe D such that when you apply G to D, this is in E less than or equal to 0, and FL D in C less than or equal to 0. And then once you and then the co-connected parts then can be defined as again D in D, G of D is in E, co-connected parts, and the FR, the right adjoint of F applied to D is in C greater than equal to D. And then it's it's a good exercise if you haven't done that before to check this is a really defined T structure. And
tiny comment.
Yes.
To connect to something from the Q&A last week. So if G is like sheaves on some X, then you have an open U. C. You should imagine G is J upper star and F is I lower star.
This is exactly the next thing I'm going to talk. But anyway, I want to write it down. That's very thanks. This is a T structure on D, and of course, even the BBD was to define all this abstract nonsense was motivated by the following example, I think, is you have a topological space or any reasonable space, a closed subset I, and the open complement J, U. Then you have and in the usual, let's say topological sheaf or what, you have all the when you have all the 6 functors, you have you do get this the usual various adjunction. J lower shriek, J lower star, and they satisfy all these axioms. And then if you have then given, so the T structure, so maybe just say get the can glue any given T structure on Z, on shifts on Z, and on shifts on U to get a T structure on shifts on X. Okay, and then exactly the usual definition perverse T structure on a stratified space is defined in this way. If your space is stratified, the so-called shift here is basically, let's say, category of local system on it, and then if you specify some perverse function, you can shift the standard T structure on the category of local system to somewhere and then glue them together. That's a perverse T structure, the usual perverse T structure. And this actually happens not, you can consider not even just constructible shifts, that's okay, or all shifts, it doesn't matter. So even on the category of constructible shifts, there is already T structure. And of course, then you can apply this story to the oops. Well, okay. Ask Sarah. So ask Sarah. Okay, so back to apply to Isaac. So then this, let me just remind you, we do have the following thing. I of B lower star. And this J B upper shriek. Then it has left adjoint and right adjoint. Maybe I don't wanna, I don't write them down. So now the whole point is, then you can just apply the previous construction to this recommend to get some T structure. This actually allows one to define some perverse T structure. On Isaac. Okay? But this is not what we want. We want something different. And to explain this is, let me remind you that all these functors written here preserve compact objects. This even exists at the level of compact objects, or the adjoints. So therefore, up to incompletion, you can formally pass to the right adjoints of all these functors, then which are only defined on the big category, not the category of compact objects. But in any case, we will pass into the right adjoint to the right adjoint up to after incompletion. We will get the following thing. So then this I less than B becomes some left adjoint. The original I less than B upper star becomes something in the middle, and then there's another one, some exceptional. Sorry, this is shriek. Yes. And this is another one, which I called little flat. All right, so this is then here this JB upper shriek become left adjoint, then JB lower star becomes something in the middle, and then there's another one is this JB upper sharp. This notion introduced at the beginning, and the whole point is after pass to the right adjoint, this also form a Riemann. Okay, satisfy all the axiom you need at the very beginning. Apply the BBD's like machinery, so you can actually use this to define T structure. The funny thing is now like the open topological part looks like the closed part, and the closed part looks like the open part. Okay, so this is purely you can, as I said, this you can purely manipulate at the level of categories. But in the case of actually of this shifts, this local Langlands stuff, this actually geometry also involves this passing. So I think because this is somehow when you relate to Isaac with Bang G, this is somehow it's not just this manipulation is not just a formally manipulation of categories, but it also has some geometry there. So I think maybe Ian will talk more about, might be, say something. Okay, anyway, we can, at the moment, we can just use this to define T structure. So then we just specify T structure on each strata. So, and so we just take the perverse function, take some kind of dimension function. The dimension function, which sends the strata, formally since this strata has dimension kind of which minus 2 rho nu b, then and you use this function to shift the standard T structure on each strata, which on each strata, the shifts on each strata is still representation of G, B, F. So this is representation category. So you have just the shift to the right to that degree. So then you can glue it, and we can glue it. And the glue. Then after gluing, we get this exceptional T structure. As mentioned at the very beginning. Okay, so this gives a definition and a sort of motivation. But I want to make a remark: is this procedure is not just applicable to just this setting. It's applicable to any setting you have open and closed gluing of topological space. In particular, maybe let me just say this construction applies to other settings. And I want to particularly mention one setting. This construction also applies, and that actually also explains this why I call this good filtration T structure on imperf is also kind of exceptional T structure. So let me apply to the following settings. I will consider the shifts on the affine Grassmannian, but equivalent with respect to pro unipotent, like precise equivalent shifts on the affine Grassmannian. This precise is a character on the pro unipotent radical of Iwahori, and then under this this is proved by for any coefficient. Okay. Maybe under some very mild assumption, this is proved by Bezukov, Gatsky, Merkovich, Reich, Ryder, that this is category actually is equivalent to the imperf of BG. It's just the categorical representations, okay? And of course, here, this F1 has a natural Schubert stratification given by I orbit, and but you can also apply, then it has the usual perversity structure. So under this equivalence, the usual perversity structure, there's the usual perversity structure. On the F1 on here, just gluing from closed strata, open strata, so on and so forth. This actually corresponds to the standard T structure on imperf of BG. So in other words, this equivalence, people usually call the geometric Kasselman-Shalikov, or Iwahor, I don't know. It's T-exact equivalence. However, you can also apply, this construction I illustrated. You can pass to all the gluing functor, you pass to the right adjoint and glue using this sort of change open the closed strata. And then you get this exceptional T structure. Then you can check this is exactly correspond to this good filtration T structure introduced by Frank-Schultz, and this is also this, get this, so this is a good filtration T structure. And that, for that reason, you know, at the very beginning, I also call this the T structure we defined on imperf is just the E exceptional one. Okay. All right. So that's a general discussion of the T structure. So again, it's kind of general nonsense, but then we will have some content to say. But before that, any questions about this general?
So what's the reason that that when lambda is characteristic 0, you remarked that the two T structures on the spectrum side are the same?
Yes, the point is here there's this category of shifts. There's the so-called standard for each W. The standard, the costant. Okay, actually this is parameterized by lambda. Don't just there's a costandard standard, then there's some IC extension. Psi. And in characteristic 0, it turns out all the extensions are clean. Standard and costandard are the same, actually. All the shifts, it only lives in finite dimensional part. So when you pass to the right edge, actually you won't see some shift do some wilder clean go to some infinity. So that's in general you have this, but in characteristic when lambda is QL, lambda is QL bar, these are all equivalent isomorphisms. So these are isomorphisms. And that actually, it doesn't matter when you pass to the right adjoint. But in modular coefficient, all these are different. I mean, one is this will correspond to W lambda. This corresponds to S lambda. So these are really different representations, and it will give you differences. Is that okay? Yes.
So gluing allows you to take two T structures and pass them to something.
Yes.
So you have both of them, but your I sub B is sort of unbounded.
Yes.
You don't run into any problems?
You need, for example, for doing perversity structure, one needs to be a little bit careful, but for this exceptional one, it's literally as it's written. There's no problem. Yeah.
I don't see where you start.
No, there's a closed strata. The open, yeah.
Oh, you build,
Yeah, you do.
oh, you could, yeah. You're exhausting the whole category.
Yeah. All right, okay. Now comes the proposition, but okay, actually this T structure is, what's written here is defined on the whole shifts on ISOC, but it restrict to the Tame part, because essentially I'm saying this, all these functors here also some preserve the Tame parts in some sense. So therefore you can also define this T structure restricts the T structure on the Tame parts. Okay, so when you restrict there, there's much more we can see. So let me just remind you this horizontal diagram. I have just this recall this horizontal diagram. This is delta, this is Newton. And we see the shift from Tame category is generated by pull-push from the co-stand objects. So we can do this co-standard, maybe monodromic version, once you choose the recall the whole Tame category is generated by these objects. Okay? And it turns out this proposition, let me give it a notation called, maybe it doesn't really need to introduce a notation here. So then the proposition is if you consider this exceptional T structure on the Tame part, and consider the connective part, then is generated by these objects and the n for any w in the f and y group and the n bigger than or equal to 0. So in other words, what happens is you do the horizontal transform of those co-stand object pull-push, they land in the connective part of the T structure, and you shift it to the left, whatever. Then that generates everything. Okay? And the sketch of proof is if W is of this form, U times X. So this is what I talk about in second lecture. This is some there's some particular type of W. In this case, this local Stuka has a better understanding. This is just this XU modulo some P, K, some O, maybe. Some version, I think it was, sorry, XU, not the UX. XU, sigma. So this is, let's say, S in lecture 2. So then this basically reduced to the really story. So then this pull-push, in fact, is going to be, this X will give you some Newton point B. It will be just B, IB lower star of this compact induction of this finite linguistic. Maybe, you know, if you do this monodromic version, this is some cover, so it's kind of, you need to replace the linguistic variety by some kind of cover. Okay, so you get this one. Then from this this parahoric to GBF, then appropriate shift. I don't want to get you know, it will be the shift to make everything correct. It's exactly the correct shift, and then this is really reduced to the finite. In the finite case, this the cohomology of finite linguistic variety concentrated from the below middle degree, from middle degree to below. So this is something, a classical fact.
Are they simply affine drivers?
I don't know, but I think recently there are people claiming prove this affine. Yeah, okay. When P is large enough, there was the linguistic knew it for a long time ago. There was an affine. There was a, this was an open question for a long time with this affine or not. But what's certain know for a long time, already a long time, is when U is kind of minimum length element, that was an affine. And in fact, everything can further be reduced to in that situation. Okay, so this solves, so in other words, this is that, by the way, this because here I use star extension. And if you look at the condition, when we define the connected part, I want a shrink restriction is lands in the connected part. So it's star extension, then it will satisfy this condition. So this shows that it does, here, so the important thing is we use the shrink restriction to define the connected part, not the star restriction, which was the usual people do for the, let's say, perversity structure, so on and so forth. So this actually shows this is actually in shift I sub E less than or equal to 0. Okay, so this is this shift is exactly correct shift to make this work. Okay, so then you can shift it to the left to make it connect part. This is for particular W, general W. Is this the linguistic reduction method? Okay, so I outline in the lecture 2. If you have a element that can be element in the affine group can be conjugated by simple reflection to reduce the length, you will be able to do something. So that's kind of you keep track, do a little bit more careful than what I did in lecture 2 to keep track of everything. You get this. All right, so in other words, we have very kind of good control of what this T structure looks like in the case of, at least in the Tame part. So it's connected parts can be explicitly, generators can be given explicitly, although a co-connected part is more complicated. Then the other thing, another result I want to mention is that now, because I don't know if this was introduced or not, the tilting sheaf on F1 flag. You didn't talk about it. So definition, sheaf F in the F1 heck category is called, what's called maybe I use slight different version of with Arnold's is co-free monodromic tilting. If it admits a finite filtration by co-standard, this so-called, this co-free monodromic, and a finite filtration by standard objects. So it admits filtration by both standard and co-standard. So these are some remarkable collection of objects in this Higgs category. It has some very nice, when you in particular talk about the T structure, it has some very nice properties. For example, the convolution is always exact, although the general convolution of two sheaves in the affine Higgs category is not exact. So that's the reason you really need to define the Higgs category as a derived category, not just an abelian category. Co-free monodromic tilting sheaf. Okay, and then we have the following proposition. Actually, we can give and by the way, this also it turns out there's a non-trivial argument to say, oh, the tilting sheaf does exist, and actually, the collection of tilting shift also generated the category in a appropriate sense. Okay, and then the proposition is if you just consider all this tilting. Oh, sorry, not Q. So let's denote by Newton of tiltings, free monodromic tilting. Shifts. Actually, you just consider this, or you push do horizontal transform of free monodromic tiltings. This form a set of compact projective generators of the abelian category of shifts. So once we have defined the T structure, we have the abelian category of shifts on Tame part on ISOC, and this is actually a very nice abelian category that has you can write on compact projective generators. Okay, and maybe a remark is a finite dimensional analog, meaning replace loop group by just a finite group. This type is the Lustig setting was obtained, I think, independent by Arnold and myself. Okay, so we do actually show that you can also do this the Lustig induction of a tilting shift in the finite head category that gives the projective generators of representation category of finite group D type. Of course, that in the finite case, when the coefficients QL, this is not really say much because the category is semi-simple. That the part is only really interesting in the modular coefficient case. But in the affine situation, even QL coefficient is very interesting because this category is far from being semi-simple. Okay, so what time? All right, I have 15 minutes. All right, so this is all I want to say about this category. Define this new T structure on shifts on ISOC Tame, and discuss something about its abelian category. Maybe I don't want to write anything, but just mention, because what happens, the proof of this proposition is somehow one can show this every co-standard admits kind of a resolution by tilting, and using what's known there, one can, there's some non-trivial arguments there, but I think it's conceivable at least, because tilting has a filtration by co-standard, and co-standard when you do horizontal transform lands in the connective parts. It has also filtration by standard. Okay, naively you may think you do horizontal transform standard, it lands in some co-connective part, so you get what you want. It's not that simple, but anyway, I think it's ideally, it's conceivable. I hope it's the case. 3. Let's talk about this C psi. So let me remind you this was maybe just a coarse Langlands functor. Maybe actually before I forget, is actually I could already see a corollary of the main theorem. So maybe another is a corollary if I didn't get there at the end, so at least I want to state the following corollary of the main theorem. And plus this proposition. It's a proposition of A, let's call. This is this corollary of main theorem plus it's this following theorem. Is before is if you apply let lambda to be QL bar. Okay, so this is the work, and if you consider pi is a representation of sorry, let me just say fix let P in GB be a parahoric. Let's fix B basic. P is a parahoric, and the pi is an irreducible representation of the Levy quotient. Like this, LP. So this is a Levy quotient. So this is a finite group of Lie type. You get the, so then you can consider compact induction. You can inflate this pi as a representation of P, and then do the compact induction. So these are like some compact objects in the category of in sheaves on Isaac. Okay. Sorry, and then you further extend it, shrink or style, it doesn't matter because this is basic strata. So these are like some compact object in this category of sheaves on Isaac. Then you can apply L psi Tame to it. So you will get a priori get some incoherent sheaf, but in the because this compact object, this is a coherent sheaf. This on here. A priori is a complex, but actually turns out it's in the heart of the usual T structure. So this is the heart of the usual T structure. But recall, because in characteristic 0, actually, quasi-co, this exceptional T structure and the usual T structure coincide, so it's just the same. Okay, let me just sketch up. This was proof. I proved it some like in this non-article, but now using this, there's a easier. I mean, better. I mean, it's not better, but it's more conceptual. So the point is, proof is pi appears as a direct summand of finite the linguistic induction of finite of a tilting sheaf on of a finite of let's see of this Levy LP. Okay, this was just to confirm this remark, like this. If you do the linguistic induction of tilting sheaves, it generates the whole representation category. So, because in the characteristic 0, every pi it appears a direct summand, and then in this basic case, you can always arrange everything nicely. So you are kind of in this situation. So then you do this. You can just regard this tilting sheaf, which is a priori in the finite head category, sits inside the affine head category. Then you do induction. So it's therefore this implies this compact induction is a direct summand of what I said, this still of some tilting, co-free tilting. Okay? And this shows that this object is in the abelian category. Okay? So this is not true if you apply push-forward lower style of arbitrary representation with GQP. This is, but for this, turns out to be in the abelian category. And then you use T exactness plus then the SIP size is exact. This shows that and the SIP size and the SIP size is equal to L psi on compacts. This shows that this guy is in the heart. Okay, so that's
Scroll up just to get to the statement of
the theorem.
The statement of the thing you just proved.
The statement of thing just proved is here. Yeah, so just you start from any representation of LP, like the finite group D type, do compact induction. For those basic ones, and then.
Sorry, maybe I didn't understand the first sentence. You say we do a delinguistic induction of a tilting sheaf of LP?
Of the Hick category of LP.
Thanks.
Yeah, so this appears a finite direction. Yeah. Yes.
Could you remark on the relationship between proposition A and the proposition above that?
Proposition A and the proposition of so proposition A will be deduced. This one, let's say, see the connected part is generated by something, and A is actually more will be deduced from this plus some other arguments. Yeah, but I didn't give you. There's some subtle arguments needed to get proposition A. Okay, yeah. And then once, so for example, particular corollaries, for example, is this coherent Springer sheaf is in the abelian category. Yeah. Know this. You have a question?
Is there any hope of using this kind of reasoning to analyze this kind of question for non-basic elements?
I think one can see something, but I haven't checked anything carefully. I was just when I was yeah.
Quantify how far it fails?
Certainly one can see something, but I haven't analyzed carefully. Yeah.
Just to make sure I understand right, you took pi to be here, but we're in characteristic 0, right? So you could just make
Everything, yeah.
finite length.
Yes.
Particularly the regular rep. So
Yes.
you could also do compact induction from like the pro-unipotent radical.
Yes, yes, yes. So in characteristic L, let's say FL, if you take pi to be the same argument works up to somewhere works if you take pi to be a projective representation. So it also kind of appears as some direct sum, so on and so forth, or maybe some of direct sum. But then the only thing I think in characteristic L was I don't know is this like something like this when like this from the incoh to imperf, how many you lose, and also this the exceptional T structure when you translate to the even if you can restrict to coh, what do you get? Yeah, this is what I don't know. Okay, but some parts of the argument certainly, like up to here is certainly okay in characteristic L if you replace pi to be some projective.
In positive characteristic, is co stable under truncations?
Under which one? You mean this?
Yeah, that's the exceptional one.
I don't think I don't think so. Yeah, like the just for BG, the perf is not like the exception T structure does not restrict. I think. Yeah. So one needs to be more careful. All right. So actually, I'm almost out of time. Maybe. 3 minutes. So maybe just to talk one thing is, at least I get here. So, so there is this local Langlands. So this, maybe I say some direct construction. Of C psi. So in fact, what's really you need is, or in some sense, or maybe some explicit formula, maybe not say direct construction, but maybe say some explicit formula, some explicit formula. This is what we need, so we need to understand this better. So for this, we need to recall that there's this action of Z from this Bezukov-Nikov's theory of central shift. Had this this actually mapped to Z, like of the Hick category. This is like a E2 center of this. Actually, this is because this is construction is certainly given by nearby cycle construction, and because so there's also actually this is image. I mean, there's it's one H. This the automorphism of these central functors. So this therefore can be. Maybe you need to do for every I, there's such thing. This can be upgraded to a functor from perf of maybe, let's say, again, I assume L is not too small. You get perf of G hat mod G hat, then go to here. Just you can upgrade. The element G hat is basically, remember the monodromy of the Tame generator. And then what you can do is then you can take the, okay, so you can, then this is kind of the one spectral action. I think Xinwen also mentioned the last week, this, but one categorical level higher thing. But then you can take taking the trace. You get the action of the perf of this log thing. Then act on this shift thing. I suck. Okay, and then this is just you get some kind of some spectral action. Of course, I mean this. This way is once what you need is just I was saying you don't need the full Bezukov-Nikov equivalence to get. You need the essential thing is you need the central functors. But of course everything is compatible. Then the C side can be written explicitly as follows. Let me just write down this and so proposition or maybe lemma. It's not really, if you give a F is inside here, because of time, yeah, maybe 2 more minutes. So yeah, maybe I say this, you get this action, and then just you should, as already in Lucas and David's lecture, once you fix some vertical object, you can use this action to define the functor from perf to the shifts on ISOC, and the C side is kind of the right adjoint. But so let me just write down an explicit formula. So F, if you give F, then inside here, the C side, you can apply it. You should get the incoherent shift, imperf on. This is supposed to be an imperf on stack of L parameters. And then how do I describe it? I take a V, a representation. This is a representation of G hat. I regard it as a vector bundle. And so then this formula is the following. Yeah, I want to take, this is a little bit hard to describe general. I need to do one more. I want to just do some special cases, just those F come from head category. This come from the pull-push procedure. Consider something like that. Then I apply C psi to these particular objects. Okay? Then you harm to it. So then this will be the same as harm of, you take, I write Iwahori Whittaker psi. This is a representation. You take I of 1 star 2 delta shrink. You apply the central functor of V dual convolved with F. Something like that. Okay, so where I double psi is the projection depth 0 part of this Whittaker psi, which is, I think, was introduced as UF, GF psi, something like that. So that's so maybe I just stop here for this, and then I'll begin next time to see a little bit how to use this formula to get the T exactness.